So yesterday we learned about limits and we started calculating some limits. And if you were in class today, hopefully you finished most of the activity where we calculated all different kinds of limits with different kinds of strategies. And this is just meant to summarize the different strategies and highlight when you use different strategies and different tips and tricks on how to calculate different kinds of limits. Okay, so the first thing we noticed, hopefully, was that direct substitution will work in a lot of cases. Now, this first one is just a notational sort of thing where we're given the function and we're finding the limit as x approaches -2 of that function. Okay, usually we just state the function in the question. So this is just sort of highlighting a different kind of notation how we might show this. So in this case, we're going to substitute, and it's x cubed plus 7x minus 1 when x approaches -2, so I'm going to sub -2 in. So this is -8 minus 14 minus 1, which should work out to -23. Now, this one I knew was going to be a direct substitute for a few reasons. One is I just know what this question is going to work out because I made it up, and so I knew it was going to work out this way. If I didn't know it was going to work out as a direct substitution, I might do it in my head, I might do it on my calculator without showing this work. I would just check and see. And again, the reason why is going to come to be more clear after the next few examples. But the other reason why I know that this is a direct substitution is I'm just thinking about this function. And I'm thinking about everything I know about functions from MHF, from last semester, and I'm thinking this is a cubic function. Well, what is the domain of a cubic function? The domain of a cubic function, of any polynomial function, is that it exists along all real numbers. And if it exists along all real numbers, then again, given what we learned about limits yesterday, we know that the limit at any point of this function will just equal the value of the function. And that may seem like a strange, if that seems like a strange statement, then we have to go back and review what a limit is. Because once we understand what a limit really is, then that statement makes a lot of sense. And because this function is continuous everywhere and it's a smooth function, it doesn't have any breaks, it doesn't have any asymptotes, it doesn't have anything funky going on, then I know I can just sub in. And I'm just going to get a number. Okay? And that's a good thing to know. That's a good level of understanding to have about limits in general. Okay? Let's take a look at this one. Now, this one is not as clear what kind of function this is, what this would look like if we sketched it. It looks to me like it has a vertical asymptote. Again, given what I know from advanced functions, the vertical asymptote would be at 0. And this question is asking the limit as x approaches 2, which is not the vertical asymptote. So there's no reason for me to think that there's anything strange happening at 2. I would imagine that at 2, there's just a smooth curve. So all we've done so far is direct substitution. But if you participate in the activity, you know that there's other things that are coming up, that are going on, that are going to be different. But even given those different kinds of questions, I can look at this, and if I have a good understanding of limits and a good understanding of the limit as x approaches 2, what that means in the bigger picture, then I can kind of tell right away that this is a direct substitution. So I'm going to directly substitute 2 plus 2 minus 4 over 2, which equals the square root of 4, which is 2 minus 4, and 2 minus 4 is negative 2 over 2, which is negative 1. So again, direct substitution worked out just fine. Okay, and as long as direct substitution works out just fine, I'm done. I've found the limit of this function as x approaches 2. I would recommend, if it's a little bit fuzzy and we're not quite sure what's happening, to go back and look at the definition and take another look at all of the ideas that we explored yesterday around limits and what their definition is. And remember, the definition of a limit as x approaches some value of a function is what value does the function approach from the left and from the right. And as long as it's approaching the same value from the left and from the right, then the limit exists and it's whatever value they're approaching. So again, I'm looking at this one. I'm looking at it. This is a very clear rational function, something we could sketch from advanced functions. It has a vertical asymptote at x equals 5, which means something strange is happening at x equals 5, but we are worried about the limit as x equals 0. So again, there's nothing in this, in all of my understanding of functions, there's nothing in this question that leads me to believe that there's something strange happening at 0. And so I'm going to try direct substitution. So subbing 0 in for x is 0 over negative 5. And there's nothing weird about that. That's just 0. And I think at this point, that might seem fine. But the strange thing is, as we move forward, a lot of people are going to think that there's something wrong with this answer. And people are going to think, oh, then the limit doesn't exist. But no, 0 is a number. So the limit exists, and the limit is equal to 0 in this case. There's nothing wrong with that. I'm going to come back to this after we've done a couple other questions, because the number 0 is pretty important when we talk about limits. And we're going to find out why. Again, if you've done the activity, you already kind of know why. But if you haven't, we're going to find out why. So on its own, this question might seem fine. 0 divided by negative 5 is equal to 0. That's a number, no problem. This limit is equal to 0. But there's a common circumstance where people might mistake this as meaning the limit doesn't exist or something else. Okay, so keep that in mind. But when you have a 0 in the numerator, nothing weird is going on, just a number, everything's good. Now, right away when I look at this question, I can see that when I have a rational function that had a vertical asymptote at 2, and I'm asking for the limit as x approaches 2. So there's a few things that could happen. Now, if you know a lot about rational functions, you would already know kind of what's happening here. But let's just ignore that for a minute and talk about the different things that could happen. I have a vertical asymptote at 2. What are all the different possibilities? I could be approaching up like that and down like that. Or, similarly, I could be approaching from the left going up and from the right going down. Or, now this function doesn't do this. And as I said, if you know a lot about these things and you're good at these things, and you already know it doesn't do this. But let's just, for example, say a different function that's a rational function could have approaching from the right going up and approaching from the left going up. And then finally, approaching from the left going down and approaching from the right going down. So those are kind of our four options. So if we look at the strict definition of a limit, it has to approach the same value from the left and from the right. So in this first case, they are definitely not approaching the value. From the left, it's approaching negative infinity, and from the right, it's approaching positive infinity. So in this case, 100%, the limit does not exist. Same thing here. From the left, we're approaching positive infinity. From the right, we're approaching negative infinity. And so the limit does not exist. Now, as we talked about, there's some debate on these two issues. And some people say that even if the limit is approaching the same infinity, positive from the left and right, some people say infinity is not a value that you're approaching and would still say that the limit does not exist. And we talked about how for us this really doesn't matter, and it's really about context, and different people have different opinions, and we're not going to worry about that. What we're going to do in this course is we're going to go with the definition as long as both left-hand limit and right-hand limit are approaching the same thing, that will be the value of the limit. So for us, we're going to say this is equal, the limit in this case is equal to positive infinity, because from the left and the right, they're both approaching positive infinity. And in this case, they're both approaching negative infinity from the left and the right. So we're going to call this, the limit would be negative infinity. So those are the four options that we're going to have. Now we want to think about this case in particular. And I want to think, are they both going up, both going down, or doing separate things? So how are we going to do that? Well, we're going to go back to advanced functions, and we're going to do asymptote testing. And so if I go just to the left of 2, 1.99, then I get a negative number here, because 1.99 minus 2 is negative. And the top is obviously positive. So from the left, I'm approaching negative infinity. Now from the right, 2.01 minus 2 is positive. So I have positive over positive. So from the right, I'm going to approach positive infinity. So it looks like this situation is this first example here. And for us, that means the limit does not exist. I'm also going to state in this case, it is since the left-hand limit does not equal the right-hand limit. So this is a bit of a different situation. It doesn't come up too much, but this is how we're going to handle this situation for us in this course. Okay, so we had 1 over 0, where we had to do some more work to determine that the limit does not exist. Again, going back above, we had 0 over negative 5. That's fine, it's just 0. Okay, and then we had the other two examples that just worked out to numbers. So now let's try this one. Now, if you look ahead, you might be suspicious about what's happening here. But I'm going to pretend that I'm not suspicious, and I'm going to go ahead and I'm going to do a direct substitution. So I get 2 times 4 squared minus 8 times 2 over 4 minus 4. 4 squared is 16. 2 times 16 is 32. 8 times, whoops, sorry, that should be a 4. 8 times 4 is 32 over 4 minus 4. And this is 0 over 0. And now a lot of people, when they go through this activity, have a lot of different ideas about what this means. Some people think it's equal to 0. Some people think it's equal to 1, because anything divided by itself is 1. Some people think it's an asymptote. If we think back to advanced functions, hopefully we can recognize that this is a hole. This is a hole in the function, and that is left to leave us wondering what's actually happening. Okay? All we know is that it's a hole, and we don't really know what the function is actually doing. So it's not 0, or at least not for sure, and it's not an asymptote, at least not for sure. We just don't know. And this is a big takeaway from today, because we call this an indeterminate limit. It means we don't know. Indeterminate means we don't know yet. It might exist or it might not. And if it exists, then that means the limit is equal to some value. And so we have to do more work to determine if the limit exists and what it is. Okay? So I'm just going to write that down. In this case, we need to do more work to figure out what's going on. Okay, and it turns out indeterminate limits are a pretty big deal. We saw these in advanced functions. When we use the difference quotient, we were actually setting things up to be indeterminate to find slopes of tangents, because we know that finding the tangent between a point and itself will give you 0 over 0. We just didn't call it an indeterminate limit. But that's what was happening. The difference here, and the reason why this doesn't feel normal, is you're not using the difference quotient. You're just given some expression that you're finding the limit of, or some function that you're finding the limit of. You're given the question. But it's actually exactly the same, or almost exactly the same as what we were doing in advanced functions. Okay? And the strategies that we've already learned apply in the exact same way. Now, some of these questions are going to look a little different and be a little bit less familiar, but we do already know these strategies. So don't forget, direct substitution was our first strategy. And if you can do that, because then you're done. But if you can't do that, if you do direct substitution, you get 0 over 0, then you have to do more work. Now, that direct substitution does not have to happen on paper. It can happen in your head. It can happen off on scrap paper. You can just do it quickly by inspection. Generally, that's what we do. We don't usually show these steps. But you want to just quickly make sure that a limit is indeterminate before you start employing the other strategies. And we've already seen that the strategy in this case is just to factor. So I'm going to kind of restart this question. So it's the limit as x approaches 4 of 2x squared minus 8x over x minus 4. Just let me double check that that's right. Okay. And as I said, this is just like advanced functions. I'm going to factor out a 2x. I'm left with x minus 4 over x minus 4. They divide. I want to see this step where you've taken out the whole and you have this final expression left. Show the substitution and then solve. And so in this case, it's equal to 8. Okay, so again, just to recap quickly, this happened because we had an indeterminate limit So we had to do more work to see if there was a limit or not and what the limit was. And in this case, our strategy was to factor. That's all we had to do. Just factor. And then the whole came out. And then we could sub in with what's left. You always end up subbing in, right? That always happens. It's just whether you can sub in at first or you have to do some work first. Okay, so here's a great example. I'm going to just do this in my head. 3 cubed is 27, minus 27 is 0. 3 minus 3 is 0. This is 0 over 0. This is definitely indeterminate. Again, the strategy here is going to be to factor. Part of what we have to learn is how to recognize different strategies. So what you do in different cases. Okay. For the most part, it's pretty obvious. So that's not really the hardest part about this, but you do want to quickly be able to determine what kind of strategy. Again, after you've already seen or by inspection, determine that this is indeterminate limit. So I have to factor the top. And if you remember from MHF, sums and difference of cubes do not go away. So this is something we still need to know how to factor. So on top, I get x minus 3. Then I get x squared plus 3x plus 9 over x minus 3. That has to happen. This is another important thing. We haven't talked about this yet. The limit as x approaches 3. So these two things that I'm going to divide out have to be both the 0 and the 0. So when I put a 3 in, I get a 0 here and I get a 0 here. So I am dividing out the whole that happens when I sub 3 in. If you divide anything else out, let's say you got an x plus 2 over an x plus 2. Well, that's not going to help in this case because that's not the whole for this limit. The limit as x approaches 3. So in this case, the limit as x approaches 3, the only thing that should be divided out is x minus 3 over x minus 3. That's the only thing that's going to let us evaluate this limit. Now, once you remember that, that's a great thing because it gives us advanced knowledge on exactly what we have to do to solve this question. We know exactly how this should play out. Okay? So I'm going to sub in now, and I got 3 squared plus 3 times 3 plus 9, which is 9 plus 9 plus 9, which is 27. Okay, so the question E was a factor, F is a factor, and I think we have one more factor here, but this one's a little bit different. We haven't seen one quite like this in MHF, although we talked about them, but we haven't quite seen it. I am going to take for granted, I've already done the math, so you'll have to trust me or you can pause and do it yourself right now, but when I sub 2 in, I definitely get 0 over 0. You can tell that the bottom is 0. Okay? When I sub 2 into the top, I get 0. We're going to do a few steps and you're going to see for sure that that's what happens. So this is indeterminate. Remember what I just said. The whole has to be when x equals 2. And what does that mean? That means the factor is x minus 2. So that means x minus 2 has to be a factor of our numerator. So in MHF, if we were going to factor a cubic, we would have to use factor theorem and start plugging in numbers and trying and looking for something that gave us a remainder of 0. 1, negative 1, 2, negative 2, 3, negative 3, and so on. But in this case, we don't have to do that because we know what our factor is going to be. So I can just force it. And I'm just going to do synthetic division with my factor as x minus 2. Now, if for some reason this didn't work out, well, then that would probably mean you don't have an indeterminate limit. And that would probably mean you didn't sub in, and you should go back and sub in and make sure this is indeterminate. Because if it's indeterminate, in this case, x minus 2 has to be a factor. So I bring the 1 down, get a negative 2. Negative 6 minus negative 2 is negative 4. Negative 4 times negative 2 is 8. 3 minus 8 is negative 5. Negative 5 times negative 2 is positive 10. Subtract, I get 0. There's my remainder. So sure enough, x minus 2 is a factor. So I'm going to come back over here. And I'm going to get x minus 2. And x squared minus 4x minus 5. The whole comes out. And again, notice, the whole is where the limit as x approaches 2. Those are both 0. That's the whole point. That has to be the thing that factors out. Now I can sub in. And this looks like 4 minus 8, which is negative 4, minus 5, which is negative 9. Okay, so there were 3 examples of factoring. This one's a little bit new. The other ones we've seen, but that's one of the strategies. And again, that's how to calculate an indeterminate limit. Hopefully, this one jumps out at us as the type of strategy that we would use. In fact, this one's easy to do to check whether or not it's indeterminate. So when I plug 0 in, I get 0 plus 2, which is 2 squared is 4. So this is 1 over 4 minus 1 over 4, which is 0. Over 0. So I can, in my head, I can check this one and see that it's 0 over 0. And so it's indeterminate. So what's our strategy for this one? Well, the other one was factor. This one, hopefully we know, is a common denominator or multiplying. There's a couple of little different ways of doing this, but common denominator is what we would call this. Okay, it's a fraction question. So I'm going to multiply the top and bottom by a common denominator of the top. And then I'm going to simplify and see how things turn out. So when I multiply this first fraction by the numerator, the x plus 2 squareds cancel out, and I just get 4. So I get 4 on top. And then when I multiply the second part by the numerator, the 4's cancel, and I get x plus 2 squared. And then on the bottom, I get x times, oops, missed the 0 there, times 4 times x plus 2 squared. Okay? Again, I know what is supposed to divide out. What has to divide out is this x, because that's what's giving me the 0 over 0, the indeterminate limit. So it's x that has to divide out. So the limit as x approaches 0. On top, I'm going to do this slowly. 4 minus x squared plus 4x plus 4 over, I'm just going to rewrite this, 4x x plus 2 squared. Now look at this. This is 4 minus 4. And then minus x squared minus 4x. So I get the limit as x approaches 0 of negative x squared minus 4x. So I've got a common denominator on top. I've simplified, expanded, simplified, done all of that. And then I'm usually left with a simple expression on top that I can factor. So you might factor out the negative as well in this case. Why not? Okay, and the x divide out. There's our whole. Again, because x approaches 0, that's what should divide out. Once we get practicing with this, we should expect that. On top, I got negative x plus 4 over 4 times x plus 2 squared. I can sub in. And I get negative 4 over 4 times 4, which is negative a quarter. Okay, so there's an example of a fraction question, common denominator question. That's one of the other strategies that we have already seen and that hopefully we're already familiar with. How about this one? Let's sub in. Put 0 in on top, I get 0. Put 0 in on bottom. 9 minus 0 is 0. 9 minus 0 is 9. 9 plus 0 is 9. Square root of 9 is 3. Square root of 9 is 3. 3 minus 3 is 0. Again, 0 over 0, indeterminate. What's our strategy this time? I think we are also familiar with this. It's multiplying by a conjugate. Notice, this was subtraction, so these are addition. But the signs inside the square root signs don't change. So this is negative, still negative. Positive, still positive. Okay? Sometimes that's a mistake that people make. Now, this is a strategy that we've seen before, so I'm going to go quickly through it. That's the common mistake, is forgetting the conjugate on top. But on bottom, I know how this is going to play out. That's the whole point. So this ends up being 9 minus x minus 9 plus x. Make sure this second part is in brackets. Okay. And the whole point is the square root signs are gone. Not in the whole question. They're still there on top, but they're gone in the bottom. 9 minus 9 is 0. Negative x minus x is negative 2x. And there's your whole. So I've got square root of 9 minus x plus the square root of 9 plus x over negative 2. Now I can sub in 9 minus 0 plus 9 plus 0 over negative 2, which is square root of 9 plus square root of 9. 3 plus 3 is 6 over negative 2, which is negative 3. Okay, and there is our first example of rationalizing. Okay, multiplying by a conjugate. couple more examples left. If you got to this one in the activity, it probably gave you a hard time because you haven't seen anything quite like this, but hopefully you got to realize that, hey, we have to rationalize the top and the bottom. Now, before I even start, what has to divide out? X minus 2 over x minus 2. I already know that. I don't know what this other junk is going to be, but I know that the x minus 2 is going to divide out because of that. That's what has to happen. This is indeterminate. We didn't do that yet. Let's do it. 2 plus 7 is 9. Square root of 9 is 3. Minus 3 is 0. 27 minus 2 is 25. Square root of 25 is 5. 5 minus 5 is 0. 0 over 0. There you go. Indeterminate as x approaches 2. At x equals 2, this is indeterminate. So we have to do some work to see if the limit exists and what the limit is. And as I said, this is what will have to happen. The x minus 2 is what has to divide out. So it turns out we have to rationalize the top and the bottom. So we're multiplying by 2 conjugates. Okay, and there you go. And I'm going to do them both at the same time. If you want to do them one at a time, that's totally fine. But once you get the hang of what a conjugate does, it's not too bad to do them both at once. I'll try to walk us through both of them happening at the same time. So when I multiply these together, I get x plus 7 times x plus 7. Sorry, square root of x plus 7 times square root of x plus 7, which is x plus 7. I know the middle term cancels out, so I'm not going to worry about that. I get negative 3 times positive 3, which is minus 9. I got to put that in brackets. Okay? And I'm left with this, the other conjugate part on top. Again, easy mistake to miss that. Next part. I'm doing this with this. Okay? So I get 5 times 5 is 25. Square root of 27 minus x times square root of 27 minus x is 27 minus x. And I'm left with the other conjugate from the first part. Now I'm going to simplify. If you're not too sure about that, go back and think about it again. Do them one at a time. But all I've done is done the conjugate on top and on bottom. You always get the other part left over. And we have to know how a conjugate works out. We can't take our time and expand this. We just need to know what it does. X plus 7 minus 9 is x minus 2. Remember what I said in the beginning. That has to happen. (25 minus 7 is negative 2. Negative x is x. Look at that. When you went through the activity and you only conjugated the top, or rationalized the top by multiplying by the conjugate, you got only x minus 2 on top. Or if you only did the bottom, you got only x minus 2 on bottom, and you thought, do we really have to do both? Well, there you go. Yes, you have to do both. That's how you get the x minus 2 on the top and the bottom. Otherwise, you got a square root sign in your way on the top or the bottom, and you can't divide out the whole. So this is a double conjugate. I've divided it out. Now I get 5 plus the square root of 27 minus x over the square root of x plus 7 plus 3. So this is 27 minus 2, which is 25. Square root of 25 is 5. 5 plus 5 is 10. I can already see it's not indeterminate anymore. So I can sub in. Whoops, not x. 5 plus 5 is 10. Uh, 3 plus 3 is 6. And 10 over 6 is 5 over 3. Okay, so it's the same strategy, just used twice. It's different. We haven't quite seen it, but it's not different in the sense that we have done this kind of thing before. We have the skills to do this. Okay, you might need to practice a little bit because it's a bit more work. Last question. If you did the activity and you experienced this one, that's the best experience you can get to learn this lesson. If you didn't do it, I'm not going to take you through that. You could pause right now and you can think about how to solve this one. But I'm not going to pretend that I don't know how to solve this one. It looks like a double conjugate. So if you haven't done this yet, pause now and try it. If you did it, you know that when you try to rationalize, nothing happens. It doesn't work out. You can't simplify. You don't get to where you want to be. Now, if that happened to you, there's a lot of great things there. I mean, there's a good lesson, but there's also the fact that you knew what was supposed to happen. You were already looking ahead. You were expecting that the whole was supposed to come out, and it didn't. And you're asking yourself, why? Well, and then we take ourselves all the way back to those first few examples when we were just substituting, before we knew anything about indeterminate limits. It wasn't that long ago. It was half an hour ago. We didn't even know what an indeterminate limit was. And all we did was substitute. And then we learned about indeterminate limits, and we realized that we have these strategies. And the three strategies are factor, common denominator, and multiplying by a conjugate. Those were our strategies. And we did them over and over and over again. And we get a question like this and we say, I know the strategy. It's multiplied by the conjugate. Then it doesn't work. And then you're stuck. And what you forgot was we only need those strategies if the limit is indeterminate. And this limit is not indeterminate. This is 3 minus 5, which is negative 2. And this is 10 minus 1, which is 9. And I'm done. And that's all there is to this question. And it's easy, really easy, to make the mistake of trying to use our strategies on a question like this that looks like it's indeterminate because it's got square root signs or something like that, and it doesn't look like those first ones. I'm going to scroll way back up. To these first ones that look like polynomials. Now that one, going back to it, yeah, maybe you would try to rationalize it. This one, polynomial, remember we said, exists everywhere. Obvious substitution. This one, if you're thinking about functions, might be an obvious substitution. But after you've done a whole bunch of indeterminate limits, and you get to one like this, it really looks like one that you have to multiply by the conjugate, but it is not. It is a substitution. So the lesson is, and hopefully if you went through the activity, you got that lesson. sub first. Okay? Hopefully that's a clear picture of the three strategies that we have already covered in advanced functions, but we're seeing them in a bit of a different picture and a couple of other little twists, the double rationalize, the factor theorem of a degree 3 polynomial kind of question. The limits are given as opposed to using the difference quotient, so things are a little bit different. And then the other big takeaway, which is sub in first. Okay, those are the takeaways from today. And then tomorrow we're going to talk about one other kind of strategy, one other kind of question, the only new kind that we're going to talk about.